Forward to the computer. Okay, so welcome to Math 150 Multivariable Calculus. This is going to be lecture 11. And what we're going to be doing today is we're going to be talking about optimization. So I'll quickly review one dimension. And maybe I will do the experiment and see if Ralph is awake, Professor Marston is awake next door. Talk a little bit about what goes on in 2 dimensions. And then for the most part, I think the video did the drowning swimmer problem. So how many of you have done index of refraction in physics? So this should look very familiar in terms of the path that the lifeguard takes is exactly what happens when light goes from one medium to another. So what I'll probably do is I'll probably do a different problem. I'll probably do the Summons maximizing product. All right, so let's review one dimension. So f prime of a is the limit as x goes to a of f of x minus f of a over x minus a. Let's say f prime of a is greater than 0. If x is greater than a and x is going down to a, what can you tell me about this ratio? What must be true about f of x minus f of a over x minus a as x goes to a from above, if f prime of a is positive? So x is really close to a, but a little bit larger than a. What must be true about the ratio if f prime of a is positive? I'm sorry? Y greater than 1? Right? Well, if x is greater than a, the denominator is positive. The limit is positive. So what do you know about the numerator? It's positive. That's all you know. You don't know anything about the magnitude. If f prime of a was 7, then eventually the numerator should be approximately 7 times the volume. But as x goes to a, since the denominator is greater than 0, the numerator must be greater than 0 when x is close to but greater than a. Thus, f of x will be greater than f of a, or x greater than a by a little. So if x is just a little bit more than a, f of x must be greater than f of a. We could also do, in this case, what happens if x is less than a and x is going to a from below. So x is now a little bit less than a and it's rising up to a. What must be true in this case? So what can you tell me about the denominator now? So the denominator is now negative. So now the denominator is less than 0, so the numerator is what? So the limit is f prime of a, which is positive. The denominator is negative. So what must be true about the numerator? Also has to be negative. So numerator is less than 0. So when x is close to but less than a, thus f of x is less than f of a, or x less than a by a little. And so what this is telling us is it's got to look something like this in the neighborhood of a. It's going to be a little bit larger to the right, a little bit smaller to the left. So cannot have a max or min at x equals a if f prime of a is greater than 0. Okay, well, this was the case of f prime of a greater than 0. What if f prime of a is less than 0? Could it have a maximum? No, it's the same argument. Similarly, no max or min if f prime of a is less than 0. I have not been doing too well with the TV shows and movies that I watch, so I will switch to literature. Greatest detective in all of fiction. No, actually, I think it's his brother Mycroft. Sherlock does go to Mycroft, but I'll accept Sherlock. Mycroft doesn't have nearly as many good managers and stories. What is Sherlock Holmes' great saying? Right. There's that. As a math professor, I would get into so much trouble if all I did from and elementarily we see the following. What's his advice?
Once you eliminate all the
Yes.
impossible things,
When you eliminate the impossible, whatever's left, however improbable, must be true. So we've eliminated, if we want to have a maximum or minimum, f prime of a being greater than 0. We've eliminated, if we want to have a maximum or minimum, f prime of a being less than 0. What's the only thing that's left? 0. So if f is differentiable and has a max or min at x equals a, then f prime of a equals 0. Is this equivalent to if f prime of a is 0, then my function has a maximum or minimum? So this statement is, if I have a maximum or minimum, then f prime of a equals 0. What if I turn it the other way around? If f prime of a is 0, then I have a maximum or minimum. Is that a true statement? So I could have a horizontal line. Technically, with a horizontal line, every point is a maximum and a minimum simultaneously. So you could actually be simultaneously a maximum and a minimum. But what we're saying right now is we have if P then Q, is this the same as if Q then P? No. So this is the difference between a necessary and a sufficient condition. If you win the Super Bowl, then you've played in the Super Bowl. You don't need to have too much football knowledge to pass this and say, okay, I can see that. Yes?
what if you win by default?
There's a lot of interesting rules as to how you do with defaults. And so then the question becomes, what do you mean by play? So if you win the Super Bowl, then you played in the Super Bowl. What about the converse? If you played in the Super Bowl, then you've won the Super Bowl. And I know my colleague, Professor Blackwood, would be a little bit upset with me for this, but the Buffalo Bills are a great example with 4 consecutive years of making it to the Super Bowl. They made it, but they never won. So you've got to be very careful about switching the order of things. So we have what's called necessary versus sufficient conditions. And so what we have here is we have a necessary condition. It is necessary that f prime of a equals 0 to have a maximum or minimum. It may be sufficient, but at this point in time, we haven't proven it. Any dodgeball fans here for the movie? What line am I thinking of? Necessary. Cultural extra credit. Nope. Now let's you try to figure out what is the line in dodgeball involving the word necessary. So right now, we know that you have to have f prime of a to be 0 to be a maximum or minimum. but it is not known yet if that is enough to force maximum minimum. So let's look at the following function. Let's look at f of x is x cubed. So if I plot this function, the plot is going to look something like this. So if f of x is x cubed, f prime of x is 3x squared. So we have a critical point at x equals 0 as f prime of 0 equals 0. This is not a max or min. So it is not a sufficient condition. All we have to do is find one situation where it fails. And the reason it fails, it's due to f double prime of x is 6x is also 0 at x equals 0. That's what's driving the problem. Okay, so we now know that if we want to find maximum minima, we look for critical points. Is there anything else we need to do? You have to look at the boundary points. And this is where I run into the wall in the video. You have to check endpoints. And the reason is, so to find max min, find critical points, check endpoints. And so if I give you, my function, here's A, here's B, and maybe it looks something like this. And I want to find the places where the first derivative is 0. So if I look for places where the first derivative is 0, okay, I get a point over here. Here's a critical point. I've actually, I think, set it up very carefully to put a critical point right here on the boundary. But neither one of those is where my function is largest. My function is largest at B. The first derivative is not 0 there. Well, the reason I can still have a maximum minimum there is because I'm not allowed to go past B. What we said is, if the first derivative is positive, you can get a little bit larger by just having time go a little bit further. Well, so long as you're allowed to let time get larger. If I can't go past B, then it doesn't matter that the first derivative is positive. It's okay, I can still have a maximum or minimum. And so I have to check this point as well. Is it a big deal checking endpoints in one dimension? Now, how many endpoints are we talking about? 2, at most. I could give you something that's from 0 to infinity, and you only have 1. Or I could give you something from minus infinity to infinity, and you have none. You have at most 2 endpoints to check. So at most 2 endpoints. That's not so bad. Now, let's say we want to do things in several variables. So now, let's say we have, continuing the football, we have an ellipse, which is approximately a football. So we'll have x over a squared plus y over b squared is less than or equal to 1. So the boundary is x over a squared plus y over b squared equals 1. And we want to find where are the candidates for the maximum and minimum of our function f of xy. So I've got some function f of xy. And I want to see where is it largest, where is it smallest. Well, let's say we have a critical point. Sorry, let's say we have a maximum over here. And we'll assume our function is differentiable. Well, I can move in the x direction. And because it's a maximum, what must be true if I move in the x direction? What must be true about the derivative at this point? I regard it just as a function of x. It's got to be 0. So we know that the partials with respect to x, df dx, at this point, let's say ab, I can't use ab because we'll use x naught, y naught, has to be 0. Because I can regard it as a function of one variable. What if I move up and down? What must be true? What's zero?
The derivative, the partial derivative.
Good, the partial derivative with respect to y has to be zero. So interior points, interior max min are where the gradient of f is equal to zero. Did I write that correctly? Did I write zero correctly?
That's the objective.
It's the zero vector. It's saying all the partial derivatives must be zero. Well, that makes sense because I can regard it just as a function of one variable if I move in a given direction. So if I want to have a maximum or minimum in the interior, I need my gradient to vanish. So this gives candidate points. These are the critical points. These are the candidates for the maximum. It again does not mean we have a maximum or minimum here. It just means we have a candidate. And now the shapes can be far more interesting in 3 dimensions. You could actually have a minimum in one direction and a maximum in the other. You have really strange things happening. Okay, and then there's the boundary. What do you think about the boundary? It's much harder. Why is the boundary harder? And the boundary wasn't a big deal in one dimension. What's the problem? Well, we had to check every value in one dimension. Why isn't it such a big deal? One dimension, but a tremendous deal in 2 dimensions. It's more than that. Yeah, there's infinitely many points to check. What is the longest song you know? Okay, how long? Hour and a half. I was going to say, if you do some meatloaf, that's around 10 to 14 minutes, depending on how much of an instrumental it has before it starts. Alice's Restaurant, it could be somewhere between 20 and 40 minutes. There's actually a song much longer than that. Infinitely many bottles of beer on the wall, infinitely many bottles of beer. Like take one down, pass it around. Infinitely many bottles of beer on the wall. You make no progress. Over here, if there's infinitely many points, unless I can find a way to check all of them efficiently and together, I'm going to be dead. So one possibility is maybe I can write the boundary as a function of one variable. And now I have a function of one variable and I can apply one variable techniques to check the boundary. So that's one possibility. The other thing which we will see later in the semester is something called Lagrange multipliers. Who here are the potential economists or econ majors? Right, so Lagrange multipliers is one of the things that you will hopefully use later in your class, and I will make sure that we cover them in great detail. All right, so what I want to do now is I want to do a good optimization problem that just really talks about how to think about mathematics, and it is a nice way to review almost everything in Calc 1, Calc 2. So here is the problem. Given a number S, divide into pieces AK such that all integers greater than 0 and the product is as large as possible. So whenever you have a problem, you always want to think about why have I put on the constraints? So I want to maximize A1 times A2 dot 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 times AN, where A1 plus A2 plus AN equals S, and N is free. I can choose how many pieces I divide it. Why do you think I'm not allowing myself to have negative pieces? To have one of the pieces being a negative number. Yeah, what if I did, consider 10 to the 100 with a negative sign minus 10 to the 100 plus 2 times 10 to the 100 plus s. What does that sum equal? Just equals s. But because I have two negative numbers, when I take the product, it reinforces. So if I could allow negative numbers, I could make this as large as I want. Okay, so that explains why I don't want negative numbers. Why don't I allow 0? So why don't I allow some of my terms to be 0? What am I trying to do? I'm trying to maximize the product. Why don't I want some of the terms to be 0? Yeah, the product would just be 0. So also, if sum AK equals 0, product equals 0. All right, so we at least now understand where these conditions are coming from. So let's try to get some sense of how these numbers could be. Do you think any of the numbers would be 1? Want to maximize the product. Okay, why would none of the numbers be 1? Yeah, multiplying by 1 is not going to help, right? So I might as well, if I have a number that's 1, just combine it with something else. So AK equals 1 doesn't help the product. So we have 2 is less than equal to each AK. Let's think about how large a number could be. Do you think any of the numbers could ever be 10? Okay, so sure, it seems like possible. But what could I replace 10 with? So let's say we had the product, let's say sum AK equals 10. I could replace it with what? What would have the same sum but a better product? Two 5s. I'm going to just do it as 2 times 8 because it's going to be 2 plus 8. Which gives 16. What if it equaled 9? What could I replace it with? It's probably the reason I wrote it as 2 plus 8 a line above. What could I replace 9 with that has a better product? 2 plus 7. I could do 8 replaced with 2 plus 6 gives 13. How much time do I need to fill up today? 2 plus 5 gives 12. 6. 2 plus 4 gives, oh, wait a minute. Sorry, this is 14. This would be 12. 10. This would be 8. So now I could do 5. Do 2 plus 3 gives 6. I'm running out of room. If I have 4, what could I replace 4 with? And what does that give? So here we're indifferent. So what we've just shown is that we're never going to have an integer larger than 4. So this gives us that AK is less equal to 4. If I had anything larger than 4 as one of my summons, if I had an 8, I could replace it with a 2 and a 6 and get something larger. know I have this product, I know each AK satisfies 2 less than equal to AK less than equal to 4. But with 4, I could do 2 plus 2, right? So I could do better. 2 less equal to AK less equal to 3. Yes.
Why are you saying AK has to be greater than or equal to 2 and not like AK needs to just be greater than?
Well, because we're assuming the AKs are integers at this point,
Oh,
right? Later, we will look at what happens when they're not integers, and this actually has applications to computer science. So this is not just a random problem. But I really want to use the time to talk about how do you think about mathematics. So the AKs are only going to be 2s and 3s. Right, that's not that many options. So only use 2s and 3s. Which do you think is better, using lots of 2s and using lots of 3s? Why? You can get more 2s for the same sum. So that's one reason why maybe 2s are better. So I need a way to compare 2s and 3s. How can I compare? Again, I only care about the sum. They have to give me a certain sum. So can you think of sums involving 2s and sums involving 3s that maybe I could compare? Okay, but there's something better than 12. 6, right? Take the simplest. So if I wanted 6, I could write that as 3 plus 3 or 2 plus 2 plus 2. What's the product? Two plus 2 plus 2, what would be the product of those 3 factors? It would be 8. What's the product of 3 and 3? 9. So it's better to have 2 3s than 3 2s. So 2 3s beats 3 2s. So you basically want to use as many 3s as you can, and if you have something left over, then you have 2s. Anybody know any interesting numbers involving or near 2 and 3? The most important numbers in all of mathematics. Pi is just over 3, so pi is not between 2 and 3. E, you know approximately what E is? 2.718281828. What is E closer to? 3. Do you think that means something, or am I just throwing a random coincidence? And again, earlier today, we were talking about necessary versus sufficient. Is this related to the value of E? Let's find out. So you had asked a good question earlier about why were we saying they were greater than or equal to 2 rather than just greater than 1? Because we had all integers. Let's just say all greater than 0. And the product is as large as possible. So now we know, say 1 less than equal to AK less than equal to 4. I know I could make it strictly greater than 1 and strictly less than 4. It's easier in mathematics if you look at what's called a closed set, where you include the endpoints. It makes it a lot easier to do the advanced analysis. So I want to figure out what's better now. And unfortunately, the simple argument I did now is much harder. So what I want to do is I want to try to figure out how to optimize in a situation like this. And again, the reason I like this is a great way for me to review a lot of the math that you hopefully see and talk about how do you attack a problem. The general idea is when you have something that's difficult, break it into something easy, solve the easy problem, and you combine them together. What makes this problem so difficult is we don't know how many pieces there are. So let's study n pieces. Do n equals 1, 2, 3, dot, dot, dot. For each n, let's figure out what the best we can do is. And then we'll look at all possible number of breaks and see which is best. All right. So again, here's my stuff. So let's do the case n equals 1. What's the best way to break up S into one piece to maximize the product? Best way to break up S into one piece to maximize the product. 1. I really have no choice. A1 equals S, done. Okay. I think the video did the Farmer Brown problem. Yes. How many people had actually read Click Clack Move? How's that type? Excellent. And the sequels were. So now let's do the case n equals 2. So I'm going to say S equals x plus y. This is really our A1 plus A2. And I want to maximize x times y, which is really A1 times A2. This should remind you of the Farmer Brown problem. So what do I have? Here's x, here's y. So the semi-perimeter is S equals x plus y is fixed. Maximize product. How do you maximize the product? So what do we do to maximize the product? What's the solution? So this was the Farmer Brown problem. I think this was the video. So what is it? X and y equal, it's a square. So let's say we have the function area of x is just x times s minus x, or sx minus x squared. So a prime of x is just going to be s minus 2x. So a prime of x equals 0 means x equals s over 2. What about the endpoints? A of 0 equals a of s halves equals 0. So max is when x equals y equals s over 2. This is the Farmer Brown problem. That if we do not have x and y equal, this is not going to be the optimal. So in the case when we have two pieces, we've already done that. What we're really doing in some sense is almost induction. Right? Any questions about n equals 2? All right, so let's look at n equals 3. So now we have n equals 3. Let's write s as x plus y plus c. So there's a couple of ways to do this. I'm going to just appeal to a result from real analysis that says if you have a continuous function on a closed bounded set, so I include the endpoints, then it takes on its maximum, it takes on its minimum. If there is a maximum and there is a minimum. What must be true? What do you think must be true at the maximum about x, y, and z? So this is where it might be a little bit vague in doing the analysis. There has to be a point where it's maximum. What do you think must be true about x, y, and z at that point? What would you conjecture? They all be equal. So assume all are not equal. Say x is less than y. Then look at x plus y over 2 plus x plus y over 2 plus z. Same sum, larger product. Because that's just the Farmer Brown problem. We just did the Farmer Brown problem on x plus y. On a known semi-perimeter, it's best when they're equal. So if x and y are not equal, we can make things larger by just replacing them with the average. And so we know there has to be some point where there's a maximum or minimum, and if they weren't all the same, then we would have a contradiction. I could always find a point that's better. So using real analysis result that a max and a min exist as have a closed set. You know, x 1 less than equal to x, y, z less than equal to 4 versus 1 strictly less than x, y, z strictly less than 4. Because I have the endpoints, I can use this result from real analysis. If I don't have the endpoints, think of the function y equals 1 over x. As you get closer and closer to 0, 1 over x is shooting up to infinity. It doesn't have to have a max. But if I force my function to be defined in the whole interval, then it has to have a max. Okay. So now, if I give you the general case, so if we have n pieces, the max is a1 equals a2 equals an equals what? So what would each piece equal if we have n pieces? S over n. So the largest product with n pieces is S over n to the n, and it ranges over the positive integers. I want to maximize this over the integers. So I want to find the maximum over n, a positive integer, of S over n to the nth power. We don't have good techniques to find the maximum over integers, right? What do we have good techniques for? What kind of functions can we find maximum for? More than just continuous. Differentiable, that was the whole point of starting today with how do we find maximum and minimum of differentiable functions. We look for the critical points and the endpoints. So I need a function of a continuous variable x that reduces to this when x is an integer. So need f that reduces to this when input is an integer. Let's try f of x equals what? What should we try for f of x? So when x is the integer n, it has to reduce to s over n to the nth power. What would you try for f of x? So what function will reduce to s over n to the n whenever x equals n? What's the simplest function you can think of? S over x to the s. And we're going to see stuff like this again when we do convergence of sequences and series later in the semester. So that's another reason why I want to spend time today. There's going to be something called the integral test. How many of you have seen the integral test in high school? Hence who's teaching. Okay. So it doesn't seem like the integral test has been done, so we will do the integral test. And you have to come up with a function to replace the sequence. And typically it's, well, wherever you see an n, put an x. So put x. Now we have a function. And we want to just find where is this function largest. So we need to maximize this function. Okay. So we want to maximize over x, the function f of x, or maximize over x, s over x to the x. And what's the range of x? How small could x be? 1. And what's the largest number of pieces we could have? We could have infinity, but we can do a little bit better than infinity. Well, actually, we could do tremendously better than infinity because any finite number is tremendously better than infinity. What? S. Because once we have S pieces, each piece is 1. If you start taking more pieces, each one is going to be less than 1. The more pieces you have, the smaller the product is. So we know x only has to go up to S. Okay. F of 1 is just going to be S. F of S is going to be 1. So those are our boundary points. And now, how do we, what else do we have to find? What else do we need? Critical points. So we need the critical points of f of x is equal to s over x to the x. I can write that as e to the x times the natural log of s over x. And if you're not sure, let's say we want to write s over x to the x as e to the g of x. Take logs. Again, in college, log is the natural log. So if we take the natural log of both sides, we get the natural log of s over x to the x equals the natural log, equals the log of e to the g of x. And another reason I want to do this problem is it allows me to review logarithms. What's the log of e to the g of x? That's just the power rule. It's just going to be g of x times the log of e. Well, what's the log of e? That's just 1. And on this side, I'm just going to get x times the natural log of s over x by the power rule. And so there's my g of x. My g of x is just x log s over x. So I can replace s over x to the x with e to the x log s over x. All right, so my function is f of x is e to the x log s over x. How do I take the derivative of this? What rule do I use? Chain rule. So when I take the derivative, oh, good. Well, the first part is just e to the x log s over x. And now I need the derivative of x log s over x. What do I do to take the derivative of that piece? Product. And so you can see, oh, wow, this is great. We get to review all these rules from derivatives. So this is just, I'm going to just rewrite this. That's just f of x, which is never 0. And now by the product rule, the derivative of x is 1 times the log of s over x plus x. Now, what's the derivative of the log of s over x? The log of s over x is the log of s minus the log of x. I get to review even more rules of logarithms. What's the derivative of the log of s? No. The derivative of the log of s with respect to x. It's 0. So the derivative is 0 minus 1 over x. So this is just f of x times the log of s over x minus 1, right? But 1 is equal to the log of what? Of e. So this is just f of x, the log of s over x minus the log of e. So this is f of x, the log of s over x times e. This is never 0. Because f of x is the exponential of something, it's never 0. So we need this to be 0. Need this to be 0. So what number, when you take the logarithm, do you get 0? So what number has 0 as its logarithm? 1. So this implies that s divided by x over e equals 1, or x is equal to s over e. That's the number of pieces. And if that's the number of pieces, how large is each piece? Each piece is s divided by s over e. Each piece is of size e. So you want each piece to be size e. That's between 2 and 3. That's consistent, good. That makes sense with what we had before. Okay. So now we have the function f of x is s over x to the x. And we know the real max is at x equals s over e. And that's going to give e to the s over e. That's going to be much, much larger than s. So this is clearly going to be the maximum. Hill's endpoints. This is the max. The problem is, this is the real max. It may not be the integer max. Remember, x has to be an integer. So maybe the integer max is nowhere near this. This allows me to review one last thing about calculus. So here's my x-axis, and here's f prime. So f of x is e to the x log s over x. F prime of x was f of x times the log of s over xe. So here's 1, here's s. My critical point was when x equals s over e. Okay. What is the value of the derivative at s over e? 0. When x is greater than s over e, what can you tell me about the sign of the derivative? So if x is greater than e, what can we say about f prime? It's s divided by x over e. When x is s over e, it's 1, 0. If x is now larger, we're now taking the log of a number that's less than 1. What's true about the log of a number less than 1? Log of a number less than 1? Negative. So the derivative is negative when you're greater than s over e. If x is less than e, now we have the log of a number that's a little bit greater than 1. What can you tell me about the log of a number that's greater than 1? Positive. So this is curve sketching. How many of you did curve sketching in calculus? So I know that my function has a critical point at 0. It's rising to s over e and then falling from that point onward. So I know the curve looks something like this. So all I have to do is check the integers on both sides immediately next to s over e. And one of them will be your maximum. And we still have like 30 seconds to speak. You've got this. This reviews so much of Calc 1 and Calc 2. More on the Calc 1 side, we're not really doing too many anti-heuristics. It reviews critical points. It reviews the chain rule, the product rule. It involves products of logarithms, the log rules, powers. Taking something that's complicated and writing it as e to the g of x, because we know how to differentiate that with the chain rule. X to the x power. We don't know what the derivative of x to the x is. But e to the x natural log of x, that we can do. So I absolutely love this problem. There's so many good things in it in terms of just trying to get a sense of optimization. And also the lesson, if something is hard, break it up into simpler tasks first. We don't know how many pieces to use, fine. Let's figure out what's the best we can do if we specify how many pieces. And then once we know that, then we'll compare all of them. All right, so this is a good place to stop. Have a good rest of the day.